Hello Math 3 to 11 students. Let's begin lesson 12, primitive roots. We're going to begin with this observation. Let m be a positive integer, and this is going to be our modulus. Then, an integer a is relatively prime to m if and only if a to the n power is congruent to 1 modulo m for some positive integer n. Here, please note that I use for some. What does that mean? Well, experienced students will see that for some corresponds to the existential quantifier when expressed in symbolic expression like this down here. In other words, there exists a certain integer n, a certain positive integer n, such that a to the nth power is congruent to 1 modulo m. So these two are equivalent. For some becomes existential. All good. Now let's go one step further. Instead of this existential quantifier expression, let's rewrite it as a non-empty set expression. In general, anytime we have an existential quantifier such as something, we can rewrite it as a non-empty set expression. What do you mean by this? So set of all possible n value or such n is non-empty. In other words, there is an element. An element exists. An element of z plus with the same condition. So you see, this existential quantifier expression and the non-empty set expression are always the same whenever we have the same condition here inside there. Most of the time we do this and we do not consider this. 99% of the time we do this, but this is one of those 1% exception that this is going to be a little bit more convenient. Why? Because we're going to define a quantity called the order of a modulo m as the minimum of this non-empty set. Remember, the set of all positive integers, z plus, is well ordered. So every non-empty subset of z plus has the smallest element, minimum. Consequently, this quantity, the order of a modulo m, is well defined if and only if the set is non-empty, which and only if a and m are relatively prime. So, if a and m are relatively prime, then the quantity, the order of a modulo m, is well defined. Otherwise, if a and m are not relatively prime, then this quantity is not well defined. It doesn't exist. Of course, in order to make this definition, we have to prove it. This is the foundation lemma that allows us to define like this. So let's prove this lemma first. This is a biconditional statement, so we have to prove both directions. The forward direction is easy. It's just an immediate application of Euler-Fermat theorem. If a and m are relatively prime, then a to the phi of m power is congruent to 1 modulo m by Euler-Fermat theorem. And of course, phi of m is a positive integer, so n value exists. If you set phi of m as my n, there could be many more, but at least one exists, and that's it. So we have one direction. Now, how about the other direction? Let's assume such n exists so that a to the nth power is congruent to 1 mod m, and then let's prove the GCD is 1. How do you prove a GCD is 1? One way to do that is to get this Bezout's linear combination expression, a times some integer plus m times another integer, add up to 1. And we are going to use this, of course. A to the nth power is congruent to 1 mod m for certain positive integer n. So start from there and use the definition of the congruence. Left hand side minus right hand side is divisible by m, so rewrite it as a to the nth power minus 1 is m times q. Q for quotient, the remainder is 0. And then from here, you see, GCD is 1, that's where we are headed. So I want to keep the right hand side equal to 1. Flip this 1 to the other side, mq to the other side, we get that. Now, see the purpose? And then, can you somehow get Bezout's linear combination expression from here? to get this GCD? Think about that. Got the idea? Stop the playback and think about it. Give up? Or did you get it? We can do it like this. A times a to the n minus 1 power, which is an integer, plus m times negative q, that too is an integer, and adding up to 1, therefore the GCD is 1. We got Bezout's linear combination expression like this. So negative q is an integer, that's easy to see because q is an integer. A to the negative n minus 1 power, a to the negative 1, a to the n minus 1 power, excuse me. A to the n minus 1 power. Is that an integer? Yes, because n is a positive integer to begin with. If I begin from n is 0, for instance, then I'm going to get a to the negative 1 power that may not exist. That may not be an integer. But I start from positive integer, so n minus 1 is non-negative, so a to the non-negative power, yeah, that's an integer. It's just a repeated multiplication of a. If n minus 1 is positive, n minus 1 is 0, then that's just 1. So in any case, this is an integer. And consequently, we have Bezout's linear combination expression, and that follows the biconditional statement. So this is true. So under this foundation, we can define the order of A modulo m as the smallest positive integer such that a to the nth power is congruent to 1 modulo m. So that's well defined if and only if a and m are relatively prime, and if a and m are not relatively prime, then the order is undefined. Alright, so much for modular order. We successfully defined it, and we also proved that it is well defined if and only if a and m are relatively prime. Now, let's consider some properties of this modular order. First, the divisibility property, next the distinctness property, and finally the GCD property. Divisibility property. A to the h power is congruent to 1 mod m if and only if k divides h. I mean, it's certain k is less than or equal to h because k, the order of a mod m, is the minimum, right? But that's too broad. We have to narrow it down further. And if I narrow it down to k divides h, then we have biconditional statement. Interesting. Okay, we'll prove that in a moment. Next. Again, a and m are relative prime, and k is the order of a mod m. Then, a to the ith power and a to the j power are congruent mod m if and only if I and j are congruent mod k. So mod m versus mod k, what's going on here? Well, here a to the i power and a to the j power. Here we do a bunch of multiplication with the same base. So the exponent rule applies. So we end up with a bunch of addition to the powers. And that's mod k. So multiplication of a to the certain power mod m can be translated to sum of addition of powers mod k. That's what this distinctness property is talking about. And then for GCD property, that's a bit tricky, so let's worry about it in the next video. Let's come back to this divisibility property and let's prove it. K is the order of a mod m. Then a to the h power is congruent to 1 mod m if and only if k divides h. By the way, in particular, k divides phi of m, and that's because this Euler-Fermat theorem is always true for phi of m. So k divides phi of m because of this divisibility property. If we prove it, of course, and we will prove it. Yeah, we will prove it shortly. Alright, let's begin. First, the proof of this opposite direction is left to the students. If k divides h, then a to the h power is congruent to 1 mod k mod m. Well, that's left to the students. Not even a hint. It's easy, so go ahead with that. And if you take any more than 1 minute, then probably you're doing it right. Probably you're doing it wrong. It should be easy. So try to complete it within 1 minute. Otherwise, you're not doing it right. The other direction is trickier. Let's talk about it. Let's assume a to the h power is congruent to 1. Yeah, here. And then we want to prove k divides h. So let's divide h by k. And let's prove the remainder is 0. Let's put it into the division algorithm. Q for quotient and R for remainder. And the remainder is always greater than or equal to 0 and strictly less than k. And from this, let's prove the remainder is 0. How do we prove that? Thanks to this computation. Well, let's look at it a little bit more carefully by taking out the higher font. Alright. A to the h power is congruent to 1. Alright, yeah, that's the starting point. And then apply this division algorithm. H is qk plus r. And then apply the exponent rule. A to the qk power times a to the r power. And then this multiplication, you can write a to the k power times q power. But a to the k power is 1. So this entire thing is 1. So we have a to the r power is congruent to 1. That's what we get. So we got that. As a result, a to the r power is congruent to 1, but r is less than k. And that gives me r is equal to 0, so 0 remainder, because otherwise k cannot be the minimum. So r has to be 0. If r is positive, then we have even smaller element than the minimum, so that's a contradiction. So remainder is 0. We must have the divisibility. How about the next property, distinctness property? Congruent mod m, if and only if congruent mod k. Well, another way to look at the same thing is incongruent mod m, if and only if incongruent mod k, by taking the counterpositive. In other words, a to the I power and a to the j power are distinct, they're different, mod m, if and only if I and j are distinct, different, mod k. That's why it is called distinctive property. And in particular, look at these. A to the 0 power, first power, second power, up to k minus 1 power, all distinct modulo m, because, look at the power, 0, 1, 2, 3 up to k minus 1 are all distinct mod k, thanks to the division algorithm. That's an application of distinctness property, and that's why it is called distinctness property. And the proof is actually amazingly simple. Without loss of generality, we can assume I is greater than or equal to j. If j is greater, then just rename it, and new j becomes I, and new I becomes j, and so that I is greater than or equal to j. And then start from this congruence, divide both by a to the j power. Then we get a to the I minus j power is congruent to 1. And we can apply the divisibility property. So k divides I minus j. And that means I and j are congruent mod k by the definition of the mod k. Everything is necessary and sufficient, so that completes the proof. Amazingly simple. But here, in the key step here, right here, I use the divisibility property. So we went through divisibility and distinctness property. As for the GCD property, that's trickier, so let's talk about it in the next video. For now, that's about it for section 1, modular order.